Good morning and welcome everyone. This is lecture number 4 in heat transfer. And we are dealing with radiation. In the previous class, we had discussed some basic points about radiation. We had seen some theorem about radiation. We had seen Kirchhoff's law. Do we remember what is Kirchhoff's law?
Yes, sir.
What is Kirchhoff's law?
At a given temperature for all bodies, ratio of their spectral emissive power to
If you
spectral.
have to read it from the sheet, even a third standard student can do it. The entire problem here is, beta, that you will not be having your notes while you are supposed to write the exam, and that is a big problem, because if your notes are not there, you will not be able to read from those notes, and you will have to rely on something known as your memory. If your memory is not working properly, that means you have not studied what we had done in the previous class. Yes or no? Have you gone through what was done in the previous class? Did you find time out of your busy schedule that you could go through your last class? Yes or no? Whatever we had discussed in the last class, did you find time to go through it? Please let me know.
No, sir.
No, sir. Well then, sir, I will give you 5 minutes here, sir, because if you don't recollect what we had done in the previous class, today's class will also go waste. So I'll now wait for 5 minutes so that all of you can go through what we had done in the previous class. Can you do that for me?
Yes, sir.
So I'll wait for 5 minutes. For 5 minutes, everyone will study and then we will start the class. Okay? 5 minutes. Move with today's class then.
Okay, sir.
So, in order to move with today's class, I'll move with some questions so that would be a sort of revision of the previous class. Here comes the first question. And the question is pretty simple. As compared to the person with white skin, the person with black skin will experience. What is the correct answer? Question number 6. 1, 2, 3, 4.
Option B, sir.
A, B, C, D. Option B, more heat and more cold. White skin will experience more heat and more cold. Why so? Why more heat and more cold?
Black body.
Black body.
Yes, sir.
Huh. More heat and more cold? Less heat and more cold, more heat and more cold, more heat and less cold, less heat and less cold. What happens with a black body? A black
Absorbs
body.
more heat.
A black body will absorb all the radiation. So when it is hot, it will absorb. But at the same time, it will also radiate at the fastest rate. Yes or no?
Yes, sir.
That means that if two bodies are at the same place, one having the same temperature, the black body will radiate more and the white body will radiate less. Yes or no?
Yes, sir.
And therefore, the answer would be more heat and more cold. Do we understand this?
Yes, sir.
Can I have some raised hands from everyone that we understand this? Such type of questions are going to come in the exam, beta. Please remember, as you can see, same question gets repeated over and over and over again. Here comes the next one. Can I have answers for this one? Material used in the manufacture of cooker, domestic cooker, should have what? Question number 11. And the answer is
A.
thermal conductivity K and specific heat S. What is
A,
the
sir.
answer? And the answer is?
A. Option A.
And the answer is A. It should have more conductivity so that it conducts very fast. It should have less specific heat so that it gets heated up very fast. Do we understand this? Yes or no? No, yes.
Yes, sir.
Pakka, sir? Let's see who gives me the answer to this one. We move on to the next question, which is question number 21. We consider the following radiation emitted by the human. Which of the following statement is true? And I wait for your answers. Who will give me the answer? We will play what you call musical chair, and I'll start from one end and every person will get a chance to answer it. So who will start? Boys will start or girls will start? Boys will start. Yes, beta. It's your turn to give me the answer to question number 21. Tell me your answer. A, B, C, D. Which one is the correct answer? Which one is your answer? The question
Kajal
passes
will-
on. Yes.
Kajal willing to answer, sir.
Yes, beta. Kajal will give the answer. A, B, C, D. Kajal, which is the one?
C, sir.
B, sir.
C, C.
C is the answer. The radiation emitted. I hope you have not seen the solution or the answer sheet, and you're not giving me the answer from the answer sheet. Yes or no?
No, sir.
That is the easiest way out. I hope you're not looking at the answer and then looking at the answer sheet and showing me and telling me the answer. Yes or no?
No, sir.
Okay, I hope that is not the case. The radiations emitted is in the infrared region. Remember, I told you, remember that sequence, because that question comes each and every time they ask you where this range lies. Do we understand this? Do we remember this?
Yes, sir.
I told you in the last class. Yes or no?
Yes, sir.
Okay. Let me see if I can have the next question. And the next question will be answered by the next girl in line. And the next girl in line happens to be Sayyada, I think so. So this is a, what do you call, a musical chair. Everyone has to give an answer. The next one is question number 33.
Sir, answer B, sir.
Sayyada is not given the answer, Kajal. Three
वो
objects.
लोग नहीं बता रहे सर.
वो लोग नहीं बता रहे, sir. Why, sir? Why are you shy in giving the answer? You're
No,
not.
no, sir.
Three objects colored black, gray, and white can withstand hostile condition up to 2800 degrees Celsius. Ooh, very hot. These objects are thrown up in a furnace where each of them attains a temperature of 2000 degrees Celsius. Which object will glow the whitest? The white, the black, all glow with equal brightness. The gray object. And the answer is B, the black object. It will absorb fastest, it will also emit fastest, and hence it will glow. Do we understand this, everyone? Can I have some reason that we understand this? Well, it seems that all of you are not good sport. If you are good sport, then you play the sport accordingly. When I say sport, I mean participation in the class is also a sport. So, let's see who gives me the answer for this one. So, from roller coaster, from musical chair, now it has become who knows the answer and who can tell me the answer. This is question number 42 coming up. A body is in thermal equilibrium with the surrounding. Tongue, 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 tongue. A, B, C, and D. Waiting for your answers. Do we have any answers for this one? It will stop emitting. Amount of radiation emitted and absorbed will be equal. It will emit radiation faster rate. It will emit radiation slowly. And the correct option is. No one knows the correct option? I'm waiting for your answer, beta.
30.
D. It will emit radiation slowly. No, that is not correct. 2, B for Bombay. The amount of radiation emitted and absorbed will be equal because the body is at a constant temperature. Whatever it is emitting, the same it is absorbing. Yes or no?
Yes, sir.
Okay, sir. Then, sir, this one, sir. Let's see who gives me the answer for this one, sir. Question number 50, we jump on to. Which of the following statement is correct for ideal black body? Is written important. Question has been repeated many times over. A, B, C, D. And the answer is option 4. It totally absorbs whatever radiation is falling on the body. Do we understand this?
Yes, sir.
Most of the question, as you can see, are theory based on what is a black body. Next one is here. If a carved black utensil is heated to high temperature and then brought in dark, so we have carving on that black utensils. So if you have this hobby of designing or painting on a utensil, you take a black utensil and you paint it. If a carved black utensil is heated to high temperature and then brought to dark, then both the carving and the utensil will shine. Only carving will shine, only utensil will shine, none of them will shine. A, B, C, D. And the option is Yes, bacha. Acha, Sayyida is talking. I can't hear you. Yes, Sayyida, tell me the answer.
A, sir.
Both utensil and his carving will shine. No, beta, carving is not a black body. It will not shine. Only the utensil will shine. It's a black body. It has absorbed a lot of heat. It will emit the fastest. So it will shine. Do we understand this? Yes or no?
Yes, sir.
Okay, sir. Okay, sir. Let me see, sir, if I can give you one or two more questions, sir. Okay, the questions are getting less and less. Let me see if I get low. A simple one here. A simple one here, and we have come too far for the simple one. This is question number 70, 70. A piece of metal and a block of wood are placed in the room. The temperature of both is 45 degrees Celsius. On touching them, what will happen? A, B, C, D. And it's a practical question. On touching them, what will happen? And the answer is question number 70 is what we are talking about.
Sir, C.
And the answer is C. Metal piece will, grammar is wrong. Will be felt. No, will be felt is correct. Grammar is also correct. Metal piece will be felt hotter than the wooden block. It doesn't look grammatically correct. So the correct grammar would be metal piece will feel hotter. Now this is not a class for English grammar. This is a class for physics. So I'll not insist much on the grammar. Metal piece will feel hotter. Why? Metal piece will feel hotter. They are at the same temperature. What is the reason? Because this could be another question that comes. Why does the metal piece feel hotter? They are at the same temperature, both of these guys.
Because of thermal conductivity, sir.
Because of high thermal conductivity, it will conduct very fast. So if you touch it, it will conduct very fast and you will feel the heat. Do we understand this?
Yes, sir.
That takes us to the next question. I would like to, since I wanted you to revise everything and you have not done it, so everything happens for good, everything happens for a reason. Because of you not revising, I am able to do these many questions. At the end of the day, some question from here will be coming in the examination hall, and this is the next one in line. A solid cube and a sphere made up of same substance and both have the same surface area. If the temperature of both the bodies is 120 degrees Celsius, now again, this I think is not what I have taught you up till now. I probably did not read the question correctly, but can you answer this one? Area has come here and you might not be conversant with the term area. So I might give this question a skip for now. I might give this question skip just now because you might not be understanding how area affects it. Well, having said that, how area affects it, let us now move on to today's topic. I think we have done enough questions. Let us now move on to today's topic. And today's topic I would have started with was Stefan's law, but now I'm having second thoughts. And since I have seen some question on Fraunhofer's line, let us start with where we had ended, and we had ended this last class with Kirchoff's law. So we will move ahead with Kirchoff's law, and here is what You must remember about Kirchhoff law. Just to give you a brief reminder, what is Kirchhoff law? At any given temperature, the ratio of, it's not a ratio actually, E lambda by A lambda for any body is constant, and that is equal to E lambda for a black body. Do we remember this? Do we remember this Kirchhoff law? Or in other words, this Kirchhoff law is telling us that A lambda, which is the spectral absorptive power, is equal to the emissivity of the body. Basically, good absorbers are good emitters and bad absorbers are bad emitters. Do we recollect this? Yes or no? And I have some reason that we understand this. What you must remember about Kirchhoff's law, point number one, you don't have to write it, you just need to mark it. For a constant temperature, the spectral emissive power of an ideal black body is constant. We know this. It has to be a constant. Spectral emissive power is a constant because at any given temperature, that is what Kirchhoff's law states. The practical confirmation of Kirchhoff's law is carried by Rishi apparatus, and the main base of this apparatus is a Leslie conductor. I have seen some question on this, so mark these two words. The main conclusion predicted from Kirchhoff's law: good absorber, good emitter, bad absorber, bad emitter, as well as this happens at low temperature as well as high temperature. I'll give you a minute to note it down. Till then, I'll go and wash up my face. I'm getting sneezes, so I'll give you a minute. I'll take that time to just wash my face, come back, note this thing down, okay? 1 minute. Okay, have you noted this down, bacha?
No, sir.
Okay, I'll give you 1 more minute. Note it down. And here we come to this particular heading, applications of Kirchhoff law. I have seen question of Fraunhofer line coming repeatedly, and that is why we are doing this. Fraunhofer lines. What are Fraunhofer lines? You will have to remember everything that I marked down now. Fraunhofer lines are dark lines in the spectrum of the sun. Sun is emitting thermal radiation. Sometimes we assume sun as a perfectly black body. Sometimes it's not a perfectly black body. In fact, an ideal black body is just not possible, but it's very near to a black body. Fraunhofer lines are dark lines in the spectrum of sun when white light emitted from the central core of the sun passes through its atmosphere, which is known as the chromosphere. You may not understand the process. Even I don't understand it. I am not a scientist. I'm a chota sa physics teacher. Radiations of these wavelengths will be absorbed by gases present, resulting in dark lines in the spectrum of the sun. So basically, sun also has an atmosphere, which is known as the chromosphere. The core of the sun is known as the photosphere, which emits this radiation, photons, photosphere. It emits the radiation. Some of these radiations are absorbed, resulting in dark lines in the spectrum of the sun. Now, what happens in case of a total solar eclipse? You might have heard, don't watch an eclipse with your naked eyes. This happens, that happens. Direct light rays emitted from the photosphere cannot reach Earth, and only rays from the chromosphere are able to reach on the Earth's surface. At that time, we observe bright, At that time, we observe bright Fraunhofer lines. So during normal condition, we have dark Fraunhofer lines. That is what you must remember. During normal condition, we have dark light, dark Fraunhofer lines under solar eclipse. In case of solar eclipse, we have bright Fraunhofer line. Why it happens? The reason is not required. You must remember this. I'll give you a minute to note it down. Are we done with Fraunhofer lines? Yes or no? Have all of you observed that Fraunhofer line? And this is what happens during normal conditions. We receive dark lines. This is the absorption spectra of the sun. During total solar eclipse, we receive direct light. And that time, we have the bright lines. Why we do not receive the direct light from the photosphere? Because it is covered by the sun. And we get this emission spectra. So during normal condition, we have absorption spectrum. Please remember this, bacha. And it is dark lines. During total solar eclipse, we have bright spectrum and we have emission spectrum. Do we understand this? These are the two things that you shall remember and never forget. I'll give you a minute to mark it and note it. Okay, then we move on to the next thing. Sand is rough and black. In deserts, I don't know whether you have been there. Daytime is very hot, nighttime is very cold. Why daytime is very hot and nighttime is very cold? Daytime, everything is absorbed by the sand. Nighttime, everything is emitted by the sand. Do we understand this? Yes or no? Good absorbers are good emitters. Note it down. Okay, then this color triangle, and you will have to remember this color triangle. Questions are coming from this color triangle. What are things you need to remember? I will underline them. What is the primary color? The color that present in the spectrum which does not get dispersed when passing through a prism is known as a primary color. What are complementary color? Two colors which when mixed produce white light is known as complementary colors. Blue and yellow are complementary. They mix, they get white light. This is the what? This is the color triangle. Red, yellow is red plus green. So if I have green here, red here, and blue here, if I mix red and blue, I will get magenta. If I mix blue and green, I will get cyan. If I mix red and green, I will get yellow. If I mix all of these, I would have the white light. Do we understand this? Yes or no? No, yes. Please draw this. Do you understand this? You'll have to remember this.
Yes, sir.
Note it down. I'll give you a minute.
No, sir.
No, sir? Okay, then I'll wait again. Okay, then let us move forward and see what type of question can come here. I hope you have drawn this. And this is why we had to do this. So I'll just note down the point in the sheet and you will see how it works into question. A green body will appear green. So you can have a question like, why does a body appear of a different color, of one particular color? Right now I'm wearing a white shirt, or in the background you can see a maroon cushion. Why does it appear in maroon or green or red or whatever? Because it reflects or transmits that color and absorbs all the other colors. Do we understand this?
Yes, sir.
When a green body is heated in a dark room, then it appears red. So red will appear green, green will appear red, yellow will appear blue, and blue will appear yellow. A red body absorbs green color strongly at room temperature. When it is heated, it will emit green light. Do we understand this? The color triangle. For a body, if it absorbs specific color radiation, if this radiation incident on the given body in a dark room, then it will appear to be black or invisible. So a red body absorbs green. If green radiation are falling on this body, it will appear black. Do we understand this? That is how things go. If you can remember this, it's very good. You can have a question on this. I'll give you a minute to note it down. And this takes us to the next big thing of this chapter, which is known as the Stefan's law. Now, we have seen the emissive power of a body or a black body. It is the amount of energy emitted by it per unit area, per unit time. Do we understand this? Now, this emissive power of the black body or any body is the amount of radiation emitted per second per unit area, which is the emissive power E. So I can write the emissive power E of a black body is directly proportional to the fourth power of its absolute temperature. Remember, temperature has to be on the Kelvin scale. So emissive power of a black body is directly proportional to T raised to the power 4, or emissive power of a black body which is the energy emitted per unit area per unit time, is equal to a constant multiplied by T raised to the power 4. This constant is known as the Stefan's constant or the Stefan Boltzmann constant. The value, remember it, it has been asked in question many times. 5.67 into 10 to the power 8 minus 8 watt per meter square, Kelvin raised to the power 4. Remember the unit as well, dimension as well. This law, which is E is equal to sigma T raised to the power 4. Remember what is E? E is the emissive power or the energy emitted per unit area per unit time. T is the temperature in Kelvin scale. Sigma is the Stefan's constant. I'll give you a minute to note it down. Do we understand this? How emissive power is related to temperature? More the temperature, emissive power becomes 4 times or raised to the power 4. Do we understand this? If I make the temperature twice, emissive power will become 2 raised to the power 4. That means 16 times. If I make the at temperature 3 times, the emissive power will become 81 times. Do we understand this? A minute to win it. Okay, then we move ahead. Remember, when we are writing it as E is equal to sigma T raised to the power 4, this law is only applicable for black bodies. But I want to make this law applicable to all bodies. How can I make this law applicable to all bodies and just not a black body? Any idea? Get idea? How can I make this law applicable to all the other bodies? Remember, Stefan's law states that emissive power of a black body is equal to sigma T raised to the power 4. Do we have any problems by this? This is only applicable for a black body, BB, ideal black body, IBB. IBB, ideal black body. This law is applicable only for an ideal black body. The emissive power of an ideal black body is equal to sigma T raised to the power 4. I want this law to be applicable to the other bodies as well. How do I do it? How do I do it? I'll give you a minute to think about it. 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 Have you thought about it? How do I make it applicable for other bodies which are not black bodies? Well, if you could not get this, it's very disappointing. But how do I make this law applicable for any other body? I go back to Kirchhoff law, and in Kirchhoff law, I had seen that E of body divided by the absorptive power of any body is equal to the emissive power of the black body. Do we remember this? We have written it in terms of spectral one. We can also write in terms of full emissive power. And we had already seen that this A, which is the absorptive power, is nothing but equal to E, small e, which is the emissivity of the body. Yes or no? This emissivity of the body lies between 0 and 1. 1 is the emissivity of a black body. Do we remember this? Yes, so from here, I can do some jiggery-piggery, and if I do some jiggery-piggery, I can write the emissive power of any body in the universe can be written as the emissivity multiplied by the emissive power of a black body of same size, same dimension at the same temperature. Do we understand this? Now I can put this in this equation, and I have the emissive power of any body can be written as E times sigma T raised to the power 4. Now this becomes a general result which is applicable to all bodies, including black body. I can also use this equation for a black body. Just I need to remember that for a black body, the value of E will be equal to 1. So this equation now becomes applicable to all bodies in the universe. Do we understand this? I will need raise hands from all of you. We have revised the entire chapter in 5 minutes because we have revised this absorptive power and emissivity and everything. I'll give you a minute to note it down. Since we have noted down what is emissive power of any general body, including a black body, now I can write how much amount of heat How much amount of thermal radiation it is going to emit in a given interval of time. How do I write it? If I write it as delta Q, which is the amount of thermal radiations emitted by this body, that will be equal to E, which is the emissive power, multiplied by the area, multiplied by the time delta T for which these emissions are radiated. If I just put the value, the total energy emitted by this body will be equal to E times sigma A T raised to the power 4 multiplied by delta T. If I just divide it by delta T, delta Q by delta T, which is the rate at which thermal radiations are emitted, will be E sigma A T raised to the power 4. This is the rate at which thermal radiations are emitted by any body, even if it's a black body or a white body or any body. We have to put the value of E. This value of E ranges from 0, which is the value of E for a pure reflector, to 1, which is the value of E for a perfect black body. Do we understand this? What are the formulas that we should remember? Formula number 1, Stefan's law. Formula number 2, modified form of Stefan's law, which is applicable to all bodies. Formula number 3, which is your Kirchoff's law. Formula number 4 is again Kirchoff's law. Formula number 5 is energy in terms of emissive power, and this formula number 6 is the rate at which energy is emitted by any body, whether it is a black or a white or a gray or anyone. Do we understand this? Mic is not working. Mic has gone. Okay, so Mike has said bye-bye to this living universe, and probably is waiting in the next universe. I'll give you a minute. We are still in this universe. We are still alive. Give you a minute to note this down. Then we move ahead in life, and this is the same thing from your sheet. That is what we were discussing. Now, in the sheet, it has been mentioned in the heading Prevost concept not applied. What do I mean when I say Prevost concept not applied? I am only thinking about the energy which is emitted by the body. Here, when we have written this Stefan's law, we have only thought about energy which is being emitted by the body. We have not thought about energy which is being absorbed by the body. Do we understand this? So the formula that we have written right now are formula for Stefan's law, where we have only understood or taken into account the energy which is emitted, but Prevost theory states that energy is also absorbed, so we have not taken that absorbed wala energy. Do we understand this? So please mention in the formula that this is the formula for Stefan's law, where Prevost concept is not applied. We have only thought about energy which is emitted. We have not thought about the part of energy which is absorbed. I'll give you a minute to note it down. Then let us move ahead. Now, what happens when you apply the Prevost concept as well? Now, if you apply this Prevost concept, and we assume that the surrounding temperature T naught is less than the temperature of the body T, so the body will be emitting it. If it is a black body, the emission will be sigma T raised to the power 4. At the same time, it will be absorbing, so it will be sigma T naught raised to the power 4. It is emitting at the rate of E1, it is absorbing at the rate of E2. So the net loss of radiation, why written loss? Because I have assumed that temperature is more. The net loss of radiation will be sigma T raised to the power 4 minus sigma T naught raised to the power 4. Do we understand this? This formula, which I am highlighting in blue, is the rate of heat lost, rate at which radiation is lost in case of a black body. If I want to make it applicable for any other body, I will multiply it by E. Here I have written the formula for energy lost by this black body if the area is A and the temperature and the time is T. Here I have written the formula for a general body which is not a black body. Here this formula is also applicable for a black body. Remember, for a black body the value of E is equal to 1. Do we understand this? Can I have some raise hand that we understand this? For a general body, the energy is E times the energy of a black body. We have already discussed this. Emissive power is E times E. The value varies from 0 to 1. I'll give you a minute to note it down. Then comes the most important part of this chapter, which is the rate at which energy or heat is lost. dq by dt or delta q by delta t. I have already given you the formula of delta q by delta t. If you talk about the formula of delta q by delta t, it was E A sigma t raised to the power 4 minus t naught raised to the power 4. Do we understand this formula? Yes or no? Raise hand will give you more confidence. They have divided it by joules, mechanical work constant. Then the answer comes in calories. In this case, the answer will be in joules per second, or this will be the unit in watts. If I want to convert it into calorie per second, they have divided it by the mechanical equivalent of heat. RH is the rate of loss of heat, or it is the rate at which a body is losing or gaining heat. Do we understand this? Now, rate of fall of temperature in degrees Celsius, how do I calculate it? I divide this by m into s, where m is the mass of the object and s is the specific heat. This J is used just for the conversion purpose. So if I divide this dq by dt by mass into specific heat, if mass is in grams and specific heat is in calorie per gram per degree Celsius, I will get the answer in per degree Celsius. If everything is in SI unit, I will get the answer in SI unit. This d theta by dt, here it was dq by dt, which is known as rate of heating. This is d theta by dt. This is rate of fall of temperature. Do we understand the difference between the two formulas? Yes or no? I'll give you a minute to note it down. Okay then. If all the parameters are same, shapes are different, rate of cooling and rate of loss of energy will be maximum in a flat surface. It will get heated and cool down very fast. Solid and hollow sphere. Solid sphere is full of material. Hollow sphere is hollow. Hollow will cool down faster. Rate of temperature fall is inversely proportional to specific heat. Specific heat is downwards. So 1 by specific heat is proportional to d theta by dt. Therefore, time, if the temperature fall is same, time is directly proportional to specific heat. If the specific heat is more, time will be more. If the specific heat is less, time will be less. Please note down these important points. Do not mark them. Note it down in your sheet. I'll give you a minute. Done this. We have seen the formula, rate at which energy is lost or rate at which temperature is lost depends on certain factors. What all it depends on? Rate of cooling by radiation, it depends on the nature, it depends on the emissivity. Emissivity is more, rate of heating or rate of cooling will be more. Area, if more is the area, it will get cooled down or heated faster, it will emit faster. Mass of the radiating body, greater the mass, slower will be the cooling. Mass is coming in the denominator. Specific heat, greater the specific heat, less will be the cooling, because specific heat is inversely rate of cooling d theta by dt. Specific heat is downwards. Temperature of the radiating body, greater the temperature, faster will be the cooling. So when the when the tea cup is hotter, it will cool down faster. When the temperature decreases, the rate of cooling also decreases. Do we understand this? Hotter cup will get colder faster. Colder cup will get colder slower because t raised to the power 4 becomes smaller. I'll give you a minute to note the other things down. Each and everything must be there in your sheet, not on the must be there in your notes, not on the sheet. And we move ahead some questions so that we can understand what we have understood today. This is a repeat of what we had probably done in the last class. Black body is A, B, C, D. Where is the mic? Mic is not working. And the answer is good absorber as well as a good emitter. Option C. Do we all understand this? Can I move ahead in life? Yes or no? No, yes. Okay, now this is the question that relates to this class, and let us see who can give me the answer to this one. For this one, we'll be doing more questions in the next class tomorrow. And in the meanwhile, what I would suggest is that you do the exercise, try to complete as many questions as you can do in the exercise, because in the next class, that is tomorrow, we would be winding up this chapter probably. The temperature of a black body becomes half of its original value. What will be the amount of radiation emitted? A, B, C, D. I have told you the answer beforehand. Who is going to give me the answer for this one? Yes. Temperature becomes half. And the answer is 1. The radiation will become 1 by 16. It is raised. The energy or emissions is proportional to t raised to the power 4. So t becomes half. So it becomes half raised to the power 4 or 1 by 16. Do we understand this? Can I have the answer for this one now? Temperature of a piece of metal is increased from 27 degrees Celsius to 327 degrees Celsius. The rate of emission of radiation by the metal will become A, B, C, D. So, what is the answer, my dear friends? And the answer is option 4, 16 times. Yes or no? The initial temperature is not 27 degrees Celsius. Remember, it's in Kelvin. It is 300 Kelvin. The final temperature is 600 Kelvin. The temperature has become twice. Temperature has become twice. Temperature has become twice. And therefore, the emission becomes 16 times. Can I have raised hands from all of you that we understand this? Kajal is sleeping in the class. No, she's there. I thought we have lost her. Lost her. What I mean by lost her, you know, lost in thoughts is what I mean by lost. Lost in thoughts and lost in thoughts. I'm not getting another word for this, but I'm waiting for another word from you on this question, which is question number 16. And I hope to get a satisfactory answer. Two bodies A and B are kept in an evacuated means vacuum, chamber at 27 degrees Celsius. The temperatures of A and B, obviously they are of the same They are of the same material, they are of the same area and all those things. The temperatures are 327 degrees Celsius and 427 degrees Celsius. What is the rate of loss of each? Of A is to B, 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 and I'll give you a minute to win it.